Hello, today I'm gonna give a short introduction to elliptic curves and projective space. So let me tell you what an elliptic curve is. So for simplicity, we assume that the characteristic of the field K over which we define it is not 2 or 3. We could also define it in characteristic 2 or 3, but we won't do this here. And we'll define it by some equation. So namely, it should be an equation of the form y squared equals to x cubed plus ax plus b. And we want one more condition, but let me first tell you a little more. So that's called the Weierstrass form of the equation. It doesn't necessarily have this form. It could have another form, and then there would have to be a transformation that gives us such a form. And yeah, you can look it up on the internet if you want to know how these transformations can look like. And also one could define it more algebraically as a curve, so a smooth curve of genus 1, I guess. I'm not exactly sure, but well, therefore you need to know what the genus is and stuff like that. So we will do it a little bit more elementary. Okay, so let's see. So at first we can write the elliptic curve, as the zero of a polynomial in two variables, namely y squared minus x cubed minus ax minus b. And as I said, we want to impose one more restriction. This is for smoothness. So an elliptic curve would have a singular point if so f of xy was 0, and also df after dy was 0, and the partial with respect to x of f was 0. So if all these equations are 0, then we would have a singular point. So let's see, let's put them all to 0. So if this is 0, then we have characteristic not equal to 2. So we would get that y is equal to 0. And so let me write it. So we want for a singular point xy, and we want to impose a condition which gives us that this curve doesn't have any singular point. Okay, so y would be 0, and minus 3x cubed would be a, and also minus x cubed minus ax would be b, because y would be 0 from before. Okay, so these are our equations. So let's see what we can do with them. So what we'll do is we put this equation into this one. So we get minus 3x squared is a, and then we would have, so let's see, we have minus x squared, so we have an x, so we have 1/3 x and x a minus ax would be b. So this gives us minus 2/3 x equal to ax equal to b, which gives us, well, x equal to minus 3/2 b divided by a, provided that a is non-zero, of course, but the case a equal to b equal to 0 is actually so gives us the same result, because if we see that later, but if a is 0, then x would be 0, and then b would also be 0. And we'll see later that the condition we impose will also cover the case a equal 0. Okay, so now we have basically two equations. We have this equation and we have this equation. So let's put them together. So we get minus 3 and then 9/4 b squared over a squared is equal to a. Oops. That's a square. We'll later have a cube. So what we get is that minus 27 b squared is equal to 4a cubed, which gives us that 4a cubed plus 27b squared is equal to 0. That's what we want. So for the curve to be non-singular, we impose the restriction that 4a cubed plus 27b squared is not 0. Okay, and now let's draw some pictures. So an elliptic curve, so in real space it can look, for instance, something like, let's see if I can draw it. It can look something like this, or there are also other cases, so it could look something like this, and then something like this. And so over the complex numbers, it's actually a little bit easier. You can think of it as somehow as a torus, and well, that's not such a nice drawing, but I hope you know what I mean. So, well, that's a little better. And so you have points on a torus, and then there's the so-called Weierstrass p function, and this then maps these points from the torus to a kind of similar equation to this one. But yeah, we won't deal, at least in this video, with curves over the complex numbers, so I'll not go deeper into that. And let me mention another, just an example of an elliptic curve. So if we have this elliptic curve, then this is related to congruent numbers, so of triangles. So numbers, so that's something you can look up if you're interested. So there's a connection to certain triangles. Okay, so far about this. So let's go to projective space, and later we'll come back to elliptic curves. So let's take a field again, and we consider the space Kn+1, but without the 0 point. So this is the n+1. So the point which is n+1 zeros. And now let's take some points here. Again, non-zero. And we define x to be equivalent to y if and only if x is equal to some lambda y, where lambda is a invertible or non-zero element in K. Okay, and now we can define projective space in n dimensions, which is, well, there are different notations, but that's just this Kn+1 without 0 modulo the equivalence relation. And you can think of it as lines in k to the n+1. So that's just so these are, so all points on a line are identified. Okay, and let's write down some notation. So for a point in projective space, we write so with these dots. So this is a point in projective space, and also so that's the same point as, so that's of course an equivalence class. That's the same point as if we would multiply with the fixed lambda in the invertible elements of K. Okay, so far about projective space. You can think of some examples. So for instance, P1 of C would be the Riemann sphere. So that's a sphere. So that's two-dimensional, but well, one-dimensional as a complex manifold. So also this n makes sense. So that's the dimension. Okay, but now let's go back to elliptic curves. And let's look at the polynomial as follows now. Well, let me give it, let's say g of x, y, c to be y squared c minus x cubed minus ax c squared minus b c cubed. Okay, as you may have noticed, we have this f here, and here we multiply with c's. And now let me tell you why we do this. So this is a homogeneous polynomial. Homogeneous means that every term has the same degree. So all these terms have degree 3. And now let me tell you why we want to look at homogeneous polynomials. So now we go a little bit back to projective space. So if we have a homogeneous polynomial, I think you know now what I mean by it. So if we have a homogeneous polynomial, it makes sense to look for zeros in p to the n. So why does it make sense? So let's say we have a polynomial, say h, and we multiply with a fixed lambda, then we get that this is lambda to the d, where so d is the degree of h, and f of x naught to xn, and lambda again non-zero. And so we get that the left-hand side is 0 if and only if the right-hand side is 0. And that's why it makes sense to look for zeros in projective space, so it doesn't depend on this lambda. Okay, so let's go back to our elliptic curve. So g of x, y, z as above, and of course we want to look at p square, and as you might have already noticed is that if we set c to be 1, we get just the previous f back. So that's that. And also if we set c to be 0, then we get, let's look at the equation, 0 minus x cubed minus 0 minus 0. So that's minus x cubed. And if we look for zeros, then if this should be 0, then we get that x is equal to 0. So if this is 0, then we have in projective space a solution 0, y. So this is a solution of 0, y, 0, and 0, 1, 0. Okay, and what do we get from here? So from here we get that we basically have zeros of f and this point. This is called the point at infinity. So we might write infinity or also 0. We'll see later while we write 0. Okay, let me first clarify why these are all our solutions, because after all I just plugged in 0 and 1 for the c coordinate, but not anything else. But if we have g of x, y, z, then this is just so for c non-zero, then we can write so this is 0 if and only if g of x over c, y over c, c over c is 0, so where this is a 1, so we get indeed that it's enough to look at, if we look in projective space, to look at these things where c is equal to 1. Okay, and now we'll define the points of the elliptic curves. So before I said that it's just a set of x and y fulfilling this equation, but now we'll modify it a bit, namely we will set it to be the set of x, y, 1, where g of x, y, 1 is 0, and the point at infinity, so 0, 1, 0. And this is, as I mentioned before, so this is basically, let me write it in parentheses, but it corresponds 1 to 1 to the points x, y with f of x, y is equal to 0. Okay, and now let me tell you why we want this point at infinity. Because at first it might seem strange, so we have this extra point. Why would we care about it? And we care about it because of the following. So we want to define addition on this curve. So we want to add points. And so the handy thing here is, so if we, in order to define addition, we can use this point at infinity and use it as the neutral element. So that's why I called it 0. And so the point at infinity is the neutral element of the addition. And let me now give you the geometric intuition for the addition. So let's, maybe I can draw it better. Well, okay, so let's assume we have a curve here, and let's pick 2 points, let's say P and Q. And now we can put a line through P and Q, and we get a third point. So that's the important thing about projective space. So if we put a line through points on the elliptic curve, then we get a third point. Actually, we would do this in the algebraic closure of the field K, but I won't care about that too much, but I'll just give you the geometric intuition. And then we reflect the point at the y equals 0 axis, and we get here another point on the curve, which we'll define as P plus Q. And also, so that we get a third point is also not strictly speaking correct. So we have to count multiplicities. So let me show you what I mean. So let's say we have a point P here and a point Q here. I hope I draw it. Okay, and let's say the line is tangent to Q. Then we would say this intersection has multiplicity 2 at Q. So Q would also be our second point. So this R from the picture above would be Q now. And so we would have P plus Q here. And the neat thing is that we can use this geometric intuition to get formulas. And what's now really nice is that these formulas also work over arbitrary fields. So we have this geometric intuition over the reals, but arbitrary fields. And the good thing is that these formulas work over any field we care about. And actually what I said above about the algebraic closure, I think that was not correct. So we would look at normally you look at curves over the algebraic closure, but in order to define addition, you don't need the algebraic closure. Okay, and now then, with these formulas, we get an abelian group. And so we can add points on this curve, and this can be quite useful. For instance, it was useful in the one video I made about this problem, which looked quite easy. So this problem here, so there you have to find points on an elliptic curve, and if you don't find good enough points, so I think we wanted a, b, and c to be bigger than 0, so integers, and if you don't find good enough points, you can still, but you have some point, you can still add them. Okay, I think that's it for today. Thanks for watching and have a good time. Bye.